Assalamualaikum and good day everyone. So today we are going into the subtopic 1.2 collision theory. So let's have a look at the learning outcome for this lesson. So there are 4 in total. So by the end of this lesson you should be able to describe effective collision by using collision theory, and then you'll be able to define activation energy, to determine the activation energy for forward and reverse reaction by using the energy profile diagram, and also to explain the transition state theory. Okay, so first, you have to know that the molecules that frequently collide with one another. So chemical reaction occur as a result of collision between reacting molecule. So as the molecule collides with one another, okay, so there are some collision that leads to the formation of new product, but there are some collision that doesn't have any effect towards the reaction. Okay, so rate of chemical reaction is directly proportional to the number of collision per time. However, in order for the reaction to occur, the collision must be what we call as the effective collision. Okay, so kita akan tengok apa effective collision lepas ni lah. Basically, as the number of collision increases, even the number of effective collision pun akan increase juga. So as you can see from here, so if the rate is fast, okay, meaning the number of effective collision is also higher. However, if the rate is slow, meaning the number of effective collision is lower then. Okay, so the collision theory is based on 3 ideas. So the first one is for the molecules must collide with one another, okay, for a reaction to occur. And the second idea is the colliding molecules must possess a certain amount of energy, meaning itu adalah activation energy sebenarnya, to initiate a chemical reaction. And then number 3, the molecule must collide in the correct orientation. Okay, tadi I mentioned about the effective collision, right? So effective collision is a collision that actually leads to the formation of new product, because if we have A and B, okay, if they collide with one another, they might stay as A and B, meaning there's no new product is formed, meaning that it's not effective collision then. However, if they collide with one another, and then you form a new product, you form C, D, E or so on, that particular collision is what we call as the effective collision. Okay, so the importance of orientation, kita akan tengoklah pasal orientation dengan pasal minimum energy tu tadi. So now kita tengok orientation dahulu. So we must also consider the orientation factor, that is how the reacting molecules are oriented relative to each other. So kita boleh tengok diagram kat sini. So as you can see here, before collision, so let's say ini adalah A, ini adalah B. Okay, this is A, this is B. So in this particular orientation here, when they collide with one another, so as you can see, you produce a new product here. Okay, so you produce C and D. Okay, meaning this is effective collision. However, if the orientation is this way, okay, ini masih lagi A and this one is still B. Okay, but now bahagian ni adalah merah, yang ni tadi bahagian ni hijau. Okay, so bila hijau bertemu hijau tu tadi, so that one is said to be in a correct orientation. Okay, so that's why you produce a new product. However, if you have a look dekat sini, so kita masih lagi ada A dengan B, tapi A ni warna hijau tu tadi. So let's say yang warna merah ni miss tunjuk guna bulat macam ni. So if they collide with one another, okay, as you can see ada collision kat sini, but somehow they stay as A and B. So this one we call as ineffective collision then, because they are not in a correct orientation. They might possess enough energy actually, okay, tapi disebabkan orientation tu salah, so tak masuk lah, dia macam puzzle lah. Okay, dia kena ada correct orientation juga, baru kamu boleh produce a new product. Okay, so you have to take note that orientation is very important. So kena dua-dua karakteristik ni dia obey, which is orientation, and also they possess minimum amount of energy, and only then it can form a new product. Okay, so activation energy pula. So in order to react, the colliding molecules must have total potential energy equal or greater than the activation energy. Okay, so what is activation energy? Okay, so basically activation energy adalah ada dekat bahagian yang paling tinggi jugalah. Dia macam as if yang the peak part of kita punya bukit kan, macam tu. So in order untuk kamu pergi to the other side of bukit, kamu kena daki bukit ni dulu kan. Okay, so you have to possess certain amount of energy untuk sampai dekat bahagian peak ni, baru kamu boleh pergi to the other side. Or else if macam energy kamu tak cukup, mungkin kamu akan patah balik. kan, kamu akan jadi semula dekat, kamu pergi balik dekat starting point kamu. So sama juga yang ni. Okay, so let's say kita start daripada reactant kat sini. So reactants nanti bila dia collide with one another, it needs to possess a certain amount of energy. It has to be equal to activation energy kat paling atas ni, ataupun more than this one here, more than the potential energy dekat bahagian atas ni, in order for it to form the new product. Okay, so what is activation energy? Activation energy is the minimum energy required to initiate the chemical reaction, or sometimes it is also defined as the minimum energy required to convert reactants to product. But usually kita akan tengok yang atas ni lah, to initiate the chemical reaction. So please remember that for a reaction between our reactants to occur, molecule must collide not only with a sufficient energy but with a proper orientation. Okay, so kalau dia dah proper orientation pun tak cukup energy, tak terhasil juga produk. Okay, kalau dia ada certain, dia dah mencapai energy yang cukup tapi not in a correct orientation, tak jadi juga produk. So dia kena dua-dua ni dia obey. It must possess enough energy and also it must collide at a correct orientation ataupun proper orientation. Okay, so let's have a look dekat transition state theory now. So transition state is the configuration of atoms of the colliding species at a time of collision. Okay, so the species formed at the transition state is called activated complex. So ada a few characteristic of activated complex kat sini yang kita kena tengok dahulu. So dekat mana transition state ni pasti mesti akan tunjuk dalam energy profile diagram. So it is a very unstable and has a short half-life, meaning kalau dia exist pun, okay, activated complex ni kalau dia exist, dia akan exist tapi very sekejap je, because it is very unstable and it has a short half-life, meaning half-life ni masa adalah masa yang dia wujud tu. And the potential energy is greater than the reactants or product. Okay, and the activated complex and the reactants are in a chemical equilibrium, and also it decomposes to form products or reactant. So daripada reactant kita akan menghasilkan activated complex, and then bila dah terhasil activated complex ni, it might goes back to reactant, but it might goes to produce a new product. Okay, so sebab tu dia kata dia akan decompose to form products or reactant. So kita tengok example kat sini. Okay kelas, so yang ni, this part here, this diagram dekat atas ni is what we call as the energy profile diagram. Sometimes it is also called as energy profile diagram ataupun reaction diagram, reaction profile diagram. Okay, reaction profile. So dekat sebelah kiri, the y-axis, kita ada energy ataupun kadang-kadang kita panggil ni sebagai potential energy. So most of the time kamu akan nampak dia sebagai potential energy. And dekat bawah tu pula x-axis kita panggil sebagai course of reaction, ataupun kalau bukan guna course pun kita boleh guna progress of the reaction, ataupun kita boleh panggil sebagai progress pathway. Okay, so ada banyak nama lah untuk Y dengan X-axis kat sini. Okay, jadi dekat mana transition state ni? So transition state berada dekat the peak part of the hills ni. Okay, kita punya energy kat sini. So atas sekali, atas activation energy ni. So ini adalah transition state. So dekat transition state ni nanti yang kita ada species yang kita panggil sebagai activated complex tadi. Okay, so for example here, ini adalah kita punya reactant class. So kita ada hydroxide dengan bromomethane. So ini adalah OH, okay, OH ion. And then kita ada bromomethane dekat sini. So this is our C, and then kita ada 3H with Br. Okay, so kita ada dua reactant ni. And then bila dia berada dekat the peak part of activation energy ni, yang atas sekali ni, okay, so now kita akan hasilkan something yang kita panggil sebagai activated complex ni tadi, activated complex, whereby sebenarnya yang ni mungkin tak clear sangat, so I'm gonna show to you dekat bahagian atas ni. Okay, Miss lukis kat atas ni. So apa yang berlaku adalah O dia akan attach kepada carbon. Okay, so masih lagi kita ada hydrogen. Okay, so atas tu hydrogen lah. Hydrogen Miss tak tanda lah, Miss letak guna bond je. Okay, and then dengan Br pun. Okay, so kalau kita nampak ni, OH ni, O dengan C ni guna dotted lines. Okay, untuk tunjukkan dia dah macam dah nak masuk gabung dengan C tu. Meanwhile antara C dengan BR pun kita akan guna dotted lines juga, sebab BR tu mungkin akan dilepaskan. Okay, so ini dipanggil sebagai the activated complex. So activated complex kita rupa macam ni lah. Dia akan ada garisan putus yang untuk menunjukkan a new bond is formed. Akan ada garisan putus yang untuk tunjuk that the bond might be akan putus lepas ni. Okay, so ini dipanggil activated complex. And then kalau dia dapat menghasilkan, so activated complex tadi kan dia akan decompose either jadi reactant balik, or it might decompose into a new product, right? So kalau dia decompose into new product, so now you get a new product here. Kamu akan dapat ini. So kamu akan dapat Br minus. Meanwhile OH now dah attach kepada kita punya C kat sini. So kita dapat methanol. Okay, so now kita dapat a new product methanol dengan bromide kat sini. So methanol pula macam ni lah rupa dia. Kalau mesti ikut lukisan ni, so something like this. Okay, so this energy profile diagram here lebih kepada Miss nak fokus dengan yang kita punya transition state theory tu tadi. So transition state theory kita ada activated complex tu tadi. So activated complex ni, okay, yang dia adalah dekat bahagian tengah-tengah lah antara kita punya reactant kepada produk. Okay, so itu dia dipanggil transition sebab dia transition nak ke arah ke produk. So it is very unstable. Okay, one thing yang kamu nak ingat adalah it is very unstable and the half-life is very short. Okay, so sebab tu dia akan berada sekejap ya. Bila dia exist sebagai activated complex, dia akan decompose straight away, whether back to reactant or going to menghasilkan a new product. Okay, so now reaction profile. Okay, so ada dua jenis reaction class. Kita belajar pasal exothermic reaction and also endothermic reaction. So kita nak kena belajar pasal reaction profile for both reaction then. Okay, reaction profile ni meaning the energy profile diagram lah. Okay, energy profile diagram. So for example, if we have carbon monoxide with nitrogen dioxide producing carbon dioxide and also nitrogen oxide. Okay, so this would be sort of dia punya energy profile diagram ataupun reaction profile, whereby you have the potential energy on your y-axis, the progress of reaction on your x-axis. Okay, and then kalau exothermic reaction ni kan, exothermic reactants punya energy is higher compared to product punya energy. So reactant tinggi, produk punya energy rendah. So lukis dulu kamu punya reactant tinggi, produk rendah macam tu, and then kamu just lukis the hill lah. Okay, so this is your reactant here, and then kamu ada hill kamu kat sini, and then kamu punya produk kat sini. So usually orang akan tulis selain pada tulis reactant, memang kita akan tulis macam ni. Tapi tak perlu lukis bulat-bulat macam ni, tak perlu. Okay, cukup untuk kamu tulis, kalau kamu nak tulis CO plus NO2 sahaja kat situ pun dah cukup dah. And then dekat bahagian produk ni untuk kamu tulis CO2 tambah dengan NO pun dah okey dah. Tak perlu lukis yang dalam bentuk molekul tadi. Okay, tak, memang jangan lukis macam tu. Just tulis dia punya chemical formula. Okay, and then kita lukis yang bahagian hill kat sini, and then kita ada the apa kat sini, the activated complex kat sini. Okay, so tandakan energy untuk reactant kita, tandakan juga energy untuk kita punya produk. Okay, and then between energy reactant dengan energy produk tu kita ada delta H. Delta H dekat sini bermaksud sama ada heat of reaction. Okay, kita boleh panggil ni sebagai heat of reaction or enthalpy energy. Okay, so kalau delta H untuk exothermic, it must be negative lah. Okay, untuk exo kan negative value. Okay, so untuk yang daripada reactant punya energy sampai dekat the peak part of kita punya energy profile diagram tu, yang tu adalah activation energy. Okay, tapi yang ni specifically ini adalah activation energy untuk forward reaction. daripada kita punya reactant menghasilkan produk. Okay, kalau kita tanda pula daripada produk punya energy sampailah dekat the peak part of kita punya energy profile diagram tu, itu adalah activation energy juga, but this one is for kita punya reverse reaction. Okay, so basically kelas sebenarnya delta H kat sini, lepas ni tunjuk lah delta H. Oh ya, dekat atas tu adalah the transition state, meaning this part here, this molecule here, ini adalah kita punya activated complex sebenarnya. So it might not be that clear, so let me just redraw balik. So the activated complex is actually ada dotted line sebenarnya dekat situ. Okay, and then kita ada N, and then ada, oh sorry, bukan N, O kan kat situ sebenarnya, O. Okay, and ada dotted line lagi, ada N, O. Okay, so this is the new bond that is formed, and this is the bond yang akan putus later on. Okay, untuk menghasilkan the new product kat sini. Okay, so kita tengok macam mana sebenarnya nak lukis profile diagram ni, energy profile diagram. First, draw the y-axis. Okay, tuliskan potential energy, and then the x-axis, progress of reaction, progress pathway, ataupun course of reaction. Okay, just choose one yang mana yang kamu senang nak ingat. Okay, and then since this is exothermic reaction, tadi Miss ada cakap kan, exothermic reaction, product punya reactant punya energy is higher, product punya energy is lower. Okay, so lukiskan and then just sambung, and then buat just bukit lah, mana-mana random je kamu buat. Okay, and then let's say ada specific reactant ataupun product yang dia bagi, and then you have to label it inside your energy profile diagram. Okay, so kat sini since saya tak ada bagi apa-apa, just tulis Mrs. Swiss reactant dengan product kat sini lah. Okay, and then tandakan, again sekali lagi, tandakan the reactant punya energy, tandakan juga the product punya energy. So in between those two energy, that is what we call as delta H. So delta H is actually activation energy of forward reaction minus activation energy of the reverse reaction. Okay, so this is exothermic kan. Exothermic tadi delta H kan value dia negatif kan. So as you can see, forward punya energy lagi tinggi. Wait. Oh, bukan lagi tinggi, lagi, sorry, the amount of activation, otak Miss lambat sekejap. So the amount of activation energy, sekejap kita tengok ni ya. Okay, so activation energy forward, so as you can see, activation energy forward in terms of size dia kecil ni sekejap kan. Okay, and then in terms of the activation energy untuk kita punya reverse reaction pula lagi besar. Okay, so nombor kecil tolak nombor besar, that's why you get a negative value untuk delta H. Okay, kalau untuk exothermic reaction. Okay, sekejap Miss nak betulkan balik. Potential energy of reactant, Miss takut Miss mention about activation energy, so Miss nak betulkan balik. Potential energy of reactant lagi tinggi compared to potential energy untuk kita punya produk. Okay, in terms of potential energy. Tapi in terms of activation energy untuk forward reaction, kalau dia adalah exo, lagi sikit. Okay, compared to activation energy of a reverse reaction. Oh sorry, tercover pula kat situ. So activation energy untuk reverse besar macam ni, untuk kita punya forward kecil macam ni. So untuk dapatkan delta H, it is always the activation energy of forward reaction minus activation energy of the reverse reaction. So in this particular case, that's why you get a negative value untuk delta H. Okay, so what about endo? So kita tengok endo. So endo, by now you should know that endothermic reaction, dia punya delta H adalah a positive value. Okay, so terbalik kepada kita punya exothermic. So potential energy of reactant now is lower compared to the potential energy of kita punya product. Okay, produk punya potential energy tinggi. So now bila jadi macam ni, so the activation energy untuk kita punya forward reaction tinggilah, kita punya potential energy untuk yang reverse reaction pula akan jadi rendah. Okay, so that's why delta H nanti kita akan dapat a positive value dan. Okay, so as you can see here, so the potential energy untuk forward besar macam ni kan. Okay, besar macam ni. Meanwhile kita punya potential energy untuk yang reverse reaction is only this small here. Okay, so again sekali lagi delta H kita adalah the activation energy forward minus dengan activation energy reverse. So in this particular case, forward lagi besar compared to the reverse one. So that's why you get a positive value untuk kita punya delta H kat sini. Okay, heat of reaction ataupun enthalpy energy. So ini untuk endothermic. So dia just terbalik kepada kita punya exothermic punya energy profile diagram. Okay, so let's have a look at example. Ada dua example kita akan tengok. The first one, so you have to draw a potential energy diagram for exothermic reaction. Indicate on the drawing the potential energy of the reactants and product. Okay, and then the activation energy of forward and reverse reaction, and also the heat of reaction. Heat of reaction meaning dia nak tahu delta H. Okay, so since this is exothermic reaction, dia dah mention exothermic reaction, bermaksud potential energy of reactant, is it higher ataupun lower? So it must be higher. Kalau exo, potential energy of reactant higher compared to kita punya product. Okay, so lukis dulu the y-axis and the x-axis. Labelkan, don't forget to label. Okay, and then just draw the hill part lah. Okay, whereby the reactant one must be higher, meanwhile potential energy untuk kita punya product lower. And then make sure you tandakan. Okay, tandakan. So daripada potential energy of reactant ke bahagian peak dekat sini, so that is the activation energy of forward reaction. Okay, meanwhile daripada kita punya product punya potential energy going towards the hill part of kita punya the peak of the energy profile diagram kita ni, so that should be the activation energy of the reverse reaction. Meanwhile between the potential energy of reactant and also the product, that is the heat of reaction. So basically kita dah labelkan semua. Okay, very simple kat sini. Okay, so kita tengok example 2. So example 2 is slightly different. So you are given a specific equation, A plus B producing C plus D, and then you have the enthalpy change for the forward reaction is positive 21 kilojoule per mole. Okay, so this is for the forward reaction enthalpy change. Enthalpy change meaning that is the delta H equals to positive 21 kilojoule per mole. So this is the forward reaction. Okay, bermaksud daripada A plus B producing C plus D. Okay, and then you have to and then dia bagi juga activation energy forward reaction. So EA forward reaction is 84 kilojoule per mole. Okay class. So this info here, it doesn't tell you whether dia tak terus specifically bagi tahu kat kamu it is endo ataupun exo. However, from the information given to you, you should know apa sebenarnya ini. Okay, so sebenarnya daripada delta H tu kita boleh figure out that oh this is endo, oh this is exo. So positive meaning it is endothermic reaction. Bermaksud kita punya ni activation energy forward reaction lagi besar, so it does make sense lah, lagi besar. Bermaksud kita punya reverse reaction pula sepatutnya lagi kecil dan okay, so it shows that ni endo bermaksud kita kena start from a lower potential energy and then naik atas, and the reactant kita should has a higher potential energy compared to the reactant then. Okay, so you have to sketch the reaction profile of this reaction, and then you have to identify, you have to determine the activation energy of the reverse reaction pula. So without lukis pun sebenarnya kamu boleh tahu dah macam mana nak cari. So basically tadi kita dah tahu dah delta H equals to activation energy of forward minus activation energy of reverse. So kita nak cari yang reverse reaction tu, so just rearrange balik. So first kita sketch dahululah the reaction profile of this reaction here. So macam biasa kena draw the y and x axis dahulu, potential energy, and then the x axis is the progress of reaction. Okay, so since ini adalah endo, so kita kena start daripada bawah pergi ke atas. Okay, so lebih kurang macam ni rupa dia. And since dia bagi specific reactant which is A and B, so tulis A plus B and then C plus D dekat bahagian product. Okay, and then tandakan kita punya activation energy of forward reaction kita. Okay, tandakan with the specific value terus. So EA 84 kilojoule per mole. Okay, untuk forward reaction. And then kita ada kita punya enthalpy. Enthalpy kita tadi adalah, if I'm mistaken, 21 kilojoule per mole. Okay, and then kita ada juga activation energy untuk kita punya reverse reaction. Apa dia tahu muncul ni? Okay, tapi reverse direction ni kita tak ada value lagi kan. So it's okay untuk just label macam tu sahaja. Okay, tapi sebenarnya it doesn't really make sense kan dekat sini. Okay, proper one kalau boleh try lukis yang based on macam at least adjustkan lah supaya make sense sikit kamu punya energy profile diagram ni. Sebab 21 kJ per mol ni is actually 1/4 of this one kan. Okay, so sepatutnya kalau 21 kJ per mol just besar sampai dekat sini je sebenarnya kan. Dekat this part je sebenarnya 21 kJ per mol. So sepatutnya kita drag sikit lagi kita punya yang ni pergi sampai dekat this part here. Okay, so sepatutnya kat sini kita punya EA reverse. So Miss harap kamu sendiri lukis try to follow at least ratio kamu tu betul lah. Okay. Okay, so tak habis lagi kan soalan ni tadi. Dia minta pasal yang value reverse tu tadi. So just rearrange balik kita punya formula yang delta H tu tadi. So kamu akan dapat yang EA reverse equals to the EA forward minus dengan enthalpy H. Okay, therefore we get 84 minus 21, so you get 63 kJ per mol. Okay, so we're done. So now you have to try this question here. Okay, so draw and label completely the energy profile diagram based on the given information to you in the question, and also determine the heat change for the forward direction. Okay, so that's it. Alright, thank you, bye.